Hello, my name is Teresa McBrien, and this is Zaid Kusari, and we are presenting our final project on azimuth position control of an antenna. So the goal of this project was to control the position of an antenna using various different controller schemes. We wanted to compare different types to see which one was better at reaching our desired state, achieving stability, and ideally decreasing settling time. We also want to see how the system would behave with and without noise. So here's our system. It is made up of a potentiometer to measure the actual angle of the antenna, which is then converted into voltage. The differential and power amplifier, which finds the voltage potential and amplifies the signal. And the motor and gears, which take the input voltage and makes it into rotational movement, resulting in the output theta, which is then measured by the potentiometer and which then feeds back into the system. This is the actual schematic diagram of the system with the appropriate hardware values, such as the actual gear ratios and lag found from literature. This is the transfer function for that system, with the input being the desired azimuth angle and the output being the output angle. For our simulations, we are starting at 0 degrees and our goal is 10 degrees. We did implement also random band limited white noise with covariance of 1 into the output measurement. We wanted to basically take this LTI system and evaluate 3 main types of controller schemes: PID control, model predictive control, and sliding mode control. So here's our basic potentiometer feedback system without an actual controller implemented. We personally wanted to gain more experience and confidence using Simulink to implement different controller schemes. So we went down that route for each controller type. As you can see, this is a closed loop system, even without a controller, so it does still settle around 10 degrees. The left shows the system with noise and the right shows without noise. Even without noise, it takes about 7 seconds to settle with a peak of around 13. The data with noise is also very noisy. So while it does center around 10, there is high variation in the output. So in reality, the antenna would basically be oscillating back and forth around that 10 marker, which is why we wanted to evaluate different controller schemes to see if we can improve this result.
Okay, the first control scheme we implemented was a PID. Here's the setup in Simulink. The values we used for the controller were 16, 5, and 2 for KP, KD, and KI respectively. We can see that the results from that controller with and without noise. For the case without noise, we can see that the system had a much less overshoot than the case without a controller. It reached the desired state or close to it within less time. For the case with noise, we can see that the system itself was fluctuating. The output itself was fluctuating around the desired state the whole time, with a plus or minus about 4 to 6 degrees of overshoot. The next controller scheme we tried was the sliding mode control. Sliding mode control, basically, it's a controller scheme that is currently used in the industry. It basically designed the control input, defines the sliding surface, and designed the control input to stay on that surface while tracking the desired state. The benefits of this sliding mode control is that it's robust, it's effective, and it's simple to apply. One of the main disadvantages is that it has a chattering input due to the sign change above and below the sliding surface, which can be reduced by using a saturation function, which we implemented in this controller. We can see that the output that we got was much For the case with no noise, was smoother than the PID. It did not have an overshoot, and it reached the desired state within reasonable time. For the case without with noise, we can see that there's still a fluctuation around the desired state, and with a plus or minus about 2 degrees of overshoot. After that, we went to the third method, or the control scheme, which is the model predictive control. It is an optimization method that is used based on defining a finite time horizon and computing the input for that horizon, then implementing the input of the current time step to the system, then recomputing or anticipating the next time horizon and implementing the next time slot, and so on. We can see that this controller accounts for the future events, unlike PID, which does not. The results of that controller were much better. We can see that the desired state was reached within about 1 second. Keeping in mind there was no constraints on the input. For the case with noise, we can see that the system was fluctuating around the desired state with a way less overshoot, plus or minus about half a degree at each time step. And here we can see the comparison between the 3 control schemes we implemented, and we can see by far that the MPC was the best one to use.